Hello, YouTube. Welcome to another exciting installment. Okay. All right. All right. So today's been sponsored by Rihanna. As you can see here, there's Rihanna. So you know I'm not lying. Okay, let's just get back to business. This is very similar to implicit differentiation, guys. It's almost the same, really. All we're doing now is we're just taking derivatives with respect to time. That's it. That's the only difference. So let's go right into it. It says, example 1. Assume the radius r of a sphere is differentiable function of t, and let v be the volume of the sphere. Find an equation that relates dv dt and dr dt. By chance, do you know what volume of a sphere is? Oh, man. Okay. Bless you. Make sure you know general formulas for the AP exam. They're not going to give you formulas, guys. No formulas at all. They might give you hints here and there, like volume of a sphere is this, volume of a cone is this, but don't assume that they are, so make sure you know the general ones. All right, so there it is. I'm going to take the derivative with respect to what? No, not with respect to r, with respect to t. So write dv dt equals, what's 4/3 times 3? So I write 4 pi r squared, and then right next to it I put dr dt. See how it's just like implicit? And that's it. That's all they wanted. So we're done with that one. Yay or nay? Perfect. Next one. Assume that the radius r and height h of a cone is differentiable functions of t, and let v be the volume of a cone. Find the equation that relates dv dt, dr dt, and dh dt. All right, so before we even get started, do you guys know what volume of a cone is? What is it? Oh. 1/3 pi r squared h. You can write it as pi over 3 r squared h. So there's the volume of a cone. So here's what you're going to do. I'm going to take the derivative of everything with respect to time, t. The pi over 3 is a constant. If you choose, you can group it with the r squared. I'm going to leave it alone, guys. So I'm going to do this. It's a constant, so I'm just going to leave it alone, factor it out like that. And I'm just going to focus on the inside. What rule do I got to use when I'm taking the derivative? Product. So dv dt, here's my pi over 3, which is a constant. You can group it with the r squared if you want. I'm not. I'm going to leave it in factored form. First, r squared times the derivative of the second. What's the derivative of h? 1 dh dt, because I'm taking the respect to t, not h. Plus second, h times the derivative of the first, 2r squared. Oh, 2r squared. 2r, sorry. And then dr dt. Close it. If you want to rewrite it nice and pretty, pi over 3 factored out, r squared dh dt plus 2rh dr dt. I probably should have written 2hr, but oh well, because h comes before r in the alphabet. And there it is, guys. How do we feel? All right, we're done. Let's go to example 2 and see if we can apply some of this. Ready? A spherical snowball, by the way, this is coming from UH-related rates for some of you that have already done it. A spherical snowball is melting in such a manner that its radius is changing at a constant rate. So I would write constant, decreasing from 21 centimeters to 10 centimeters in 30 minutes. At what rate is the volume of the snowball changing at the instant the radius is 3 centimeters? So here's what we're going to do, guys. Bless you, whoever sneezed or whatever it was. All right, I need to know dv dt for a sphere, a snowball. And I already did that. dv dt is 4 pi r squared. 4 pi r squared dr dt. What do I need? I need r. They give it to me, 3 centimeters. And I need dr dt, which they also give it to me. But I have to calculate it a little bit. So how do you calculate it? Well, look, I'm going from 21 centimeters to 10. So dr dt is equal to, let's see, I went negative 11 centimeters in 30 minutes. So I'm going to leave it as negative 11 over 30 because I don't know if it reduces centimeters per minute. I'm going to plug this guy in for dr dt. I'll take my calculator. I didn't turn on my laptop. Okay, I'm turning on my calculator, guys. 4 times pi times 3 squared, because it's telling me 3, times negative 11 over 30. Is it me or did it get hot really quick? Oh man. I thought it got hot relatively quick. Yeah, let's turn on the AC. No. Yeah, see, let's turn on at least one of them. Just one. Yeah, we're gonna turn on this one. No, not that one. That's fine right there. All right, so let's see. 4 times 9 times 11 over 30. And I'm going to leave it in terms of pi, guys, because pi is a perfect. Yeah, I'm just going to turn it to a negative there. So mass fraction. So let's see what this is. So when you take your UT and your UH quiz, it's going to come out like this. Your DVDT is a negative 66 pi over 5. And if you need it units, it's cubic centimeters per minute. And that's it. How do we feel, guys? All right, let's go to another one. I like this one here. This is going to be a cool problem. This one's from the textbook. You guys ready? A police cruiser approaching a right-angled intersection from the north. Okay, right-angled intersection. So here is the curve. Bird's eye view. You're a bird. You're a bird. And this guy here is the cop. That's the cop. Is chasing a speeding car that has turned the corner, now moving straight east. Okay, so here's that speeding car. This is the bad guy. When the cruiser is 0.6 miles north, so I'm going to call this X and Y. So Y is 0.6. Of the intersection of the car is 0.8 miles to the east. So X is 0.8. The police determined with radar that the distance between them and the car is increasing at 20 miles per hour. Okay. I'm going to call that Z. And the ZDT is 20 mph if you want to put units. If the cruiser is moving at 60 miles per hour at the instant measurement, what is the speed of the car? So they want to know the speed of the bad guy. And sometimes it takes like several iterations for you to read this to understand the problem. The number one mistake, guys, that you guys do is you guys put 8 where the X is at and 6 where the Y is at, or 0.6. If you do that, you're making it constant all the time. So put letters instead of numbers. Cool? And on the side, put your numbers. All right, so what do they want? They want dxdt. Bless you. That's what they want, guys.
What does it say?
dz over dt. That's the radar change. So they want dxdt. Does that make sense to everyone? So I'm going to write what I do know. How fast is the car moving? The cop car? $60 miles per hour. Do I put 60 or negative 60? The way I drew my negative, because he's going that way. So negative 60. I don't know dxdt, but I know dZdt. dZdt is 20, positive. Wait, is it positive or negative? Increasing, yep, positive. Are we still okay, guys? Okay. Before I get started, if x is 0.8 and y is 0.6, what is z? Pythagorean theorem. 0.6 is 0.36 when I square it. 0.8 is 0.64 when I square it. 64 and 36 adds up to 100, so I know that 0.64 plus 0.36 adds up to 1. Is everyone okay with how I got z equal to 1? Okay. Again, Pythagorean theorem is what relates all of them together. And I'm going to be taking the derivative with respect to what? T. So here it is. The derivative of x squared is 2x dx dt. Plus the derivative of y squared is 2y dy dt equals, and the derivative of z squared is 2z dz dt. If you want to factor out the 2 on the left and then cancel it out, you can. It makes life a little easier. I factor out a 2 on the left and then I canceled it with the 2 on the right. So what I finally have is x dx dt plus y dy dt equals z dz dt. And check it out. I have everything. I have x. I'm looking for dx dt. I have y. I have dy dt. I have z. I have dz dt. Plug everything in and solve. X was 0.8. And dx dt is what we're looking for. Plus y was 0.6. And dy dt was a negative 60. And z was a 1. And dz dt is a 20. So here we go. 0.8 dx dt plus, I want to say it's a negative 36 equals 20. 0.8 dx dt equals 36, 46, 56. How do I get dx dt by itself? Yeah. So dx dt is equal to, I don't know, 56 divided by 0.8. Let's see, 56. I want to say maybe 80 or something. 0.8. Oh, 70. I was wrong. He's going pretty fast. He's going 70 miles an hour. I would. If the cruiser is going, what is the speed of the car? I would just write the speed of the car is 70 miles per hour. For now, that's good for now. Later on, we'll be more specific, but for now, that's good. How do we feel? Good, right? Pretty cool? Or not cool? A rising balloon. For those of you that are going to be NASA engineers, you're going to be tracking stuff. You're going to have to program. This is the math that you're going to be doing, guys. Now you got to figure out how to program your laptop or computer or system to take care of all this stuff. All right, so here it is. A hot air balloon rising straight up from a level field is tracked by a rangefinder 500 feet from the liftoff point. At the moment, the rangefinder elevation angle is pi over 4, so that's equivalent to 45 degrees, but we don't work with degrees, just radians, guys. The angle is increasing at a rate of 0.14 radians per minute. How fast is the balloon rising at that moment? Yeah, that's a pretty important question. I mean, I don't know. I don't necessarily care about how fast the balloon is rising, but maybe someone else out there does. They want to know. So you have a hot air balloon. So here's my hot air balloon. Here's my right angle. And here's my rangefinder in blue. I'm going to call that theta. And the only thing that I'm going to put here is anything that is static, that does not change. So the rangefinder is how many feet away? That you can put in here from the liftoff point. All right, so what do we know so far? The angle is increasing at a rate of 0.14 radians per second. So we know d theta dt, 0.14 rads per minute. So this radical. Rad. Okay, I'll stop.
So what's the elevation?
Yeah, I want to know how fast is the balloon rising. So I'm going to call this y. So what do they want to know? dy dt. How do we feel so far, guys?
This is 0.14 what?
Radians per minute. That's all we know. All right. You can use sine, cosine, or tangent. Let's be simple. Let's use the one that uses the least amount of variables. I could use sine. I could use cosine. Well, cosine wouldn't make really sense. The easiest one for me is tangent because it takes the y into account, but it also takes the 500 into account. And the 500 is a constant. Does that make sense? So I don't have to worry about that. So I'm going to use which one? Tan. I'm going to write tan of some angle theta equals y over 500.
Wait, so does the pi over 4 not matter?
Oh, yeah, it does. That's theta. Theta is pi over 4. I'm going to need that guy.
So why haven't we just put it in power?
Oh, I can't plug in power 4 because then it makes it static. It's moving. It's a little thingy that's moving. At the moment, it's 45 degrees at that moment. Are we still okay? It's a moving on a pivot. How do we feel right now, guys? All right, I'm going to make one better. I see y over 500. I want y by itself. How do I get y by itself? Multiply both sides by what? So I'm going to write it like this. Y equals 500 tan theta. Now we're really good. It almost looks like an explicit function. It really kind of is. I'm going to be taking a derivative with respect to what letter? T, because I want dy dt. So here we go. Dy dt equals 500. What's the derivative of tangent? Secant squared theta. And am I taking the derivative with respect to theta or with respect to t? T. So what do I put right next to it? So now dy dt. D. Perfect. D theta dt. It's all good, miss. D theta dt. I got everything I need, guys. In case you don't remember, because I know sometimes we have issues here. This is the same thing as saying 500 times secant theta squared d theta dt. And look, I got everything I need. You know theta, you know d theta dt, and that's going to give us your dy dt. Where'd it go? All right, here we go. So dy dt is equal to 500 secant of pi over 4 squared times 0.14. 500 times, here comes your unit circle, it never goes away. Secant of pi over 4. They're being nice. At pi over 4, x and y are the same coordinate anyways, same magnitude. So 2 over square root of 2, and I'm going to square that sucker, and I'm going to multiply it by 0.14. Does that make sense? Does that make sense, guys? All right, finally, here's my final answer. 500 times 2 squared is 4. Square root of 2 squared is 2. 0.14. So 500. You don't have to be this specific if you just want to go right to it. So 1,000 times 0.14. I want to say that's 140. Someone check for me, just in case. No, it's 100 times 0.14. I want to say, okay, I want to say that I know how to move the decimal. And my units are feet per minute. Yeah, that sounds plausible. 140 feet per second would be pretty fast for a hot air balloon. But 140 feet in 1 minute, yeah, it's raising about, what's that, 60, 20, a little more than 2 feet per minute. Per second. Yeah, that sounds like a hot air balloon. A little faster than 2 feet per second. How do we feel, guys? Do you see how all this is really like good stuff? Yeah, it's beautiful, no? If you show this to a freshman, would they get scared? Nah, no they won't, because we're YWLA tough. We got this. All right, one more. Let's see if we can do this without errors. Water runs into a conical tank at a rate of 9 cubic feet per minute. All right, so right off the bat, I'm going to write dVdt is 9 cubic feet per minute. The tank stands point down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Oh, that sounds like a really good question. Draw a picture. I don't know, maybe you're a chemist and you have some type of fluid in here. It's being pumped in. Well, it's water, I guess, at the moment. So draw a picture. Here's my water. And let's see, how fast is the water level rising when the water is 6 feet deep? So this, I'm going to call this. The tank stands point down, has a height of 10 feet. Okay. I'm going to call this R. And I guess I'm going to call that H. All right, so let's write what we know now, guys. Water runs into conical tank, so dVdt is definitely, I already have it up there, but I'm going to rewrite it again. dVdt is 9. The tank stands point down, has a height of 10 feet, so that's my height overall. So this is the total height, and that I can write 10 because it's not changing. The cone's not morphing into something else, you know? Oh yeah, for the radius, that's not changing either, so I can put a 5 there. But this radius down here is changing. So this one, I'm going to put R. But up here, that's a 5 there. How fast is the water level rising when the water is 6 feet deep? All right, so here we go. Volume of a cone. We said pi over 3 r squared h. That's the volume of a cone. Are we still okay, guys? Yes, I have a tattoo. No, I don't. Or I do, I don't know. I don't, guys. Let's see. What was my derivative when I took it? First after the second, r squared dh dt plus second h times the derivative of the first, 2r dr dt. Close, close. So then we said dv dt rewritten pi over 3 parenthesis r squared dh dt plus 2hr dr dt. Ah, look, this time I put the h before the r. All right. What do they want? Yeah, how fast it's rising. With respect to this picture, look, I labeled it a certain letter so it could be easy to define. What do I want in terms of mathematical equations or symbols or whatever? They want perfect dHdt. They want dHdt, question mark. So let's see if I have everything I need to figure this out. Do I have the radius? Not directly, but I kind of have it. Yeah, they give me the base radius, but I need to know the water radius, like the radius of the water. I don't know dHdt, that's what I want to figure out. They tell me the height of the water, and I have the radius, not directly. I'm going to tell you how to get that. And I don't have the drdt. What's up? No, the radius is changing. The radius, if the cone was full of water, way up here, the radius is 5. But if you go down, the rate of change, the radius is getting smaller. But the water is actually going up, though, right? Because I'm putting.
So why? Okay. So then wouldn't we not have the radius? Because that's like saying we have dHdt, it's 6.
No, we have the radius. Do you guys see how we have the radius?
Yes.
Did we take? And don't worry, guys. I'm not insulting your intelligence. I promise you, I'm not. I was a geometry teacher. Did we take geometry? Say yeah. Yeah, I know you took geometry because I taught you guys geometry. You guys are the only class that I've had for 4 years. Well, that I've known for 4 years. The only group ever. All the other classes I've only known for like 2 years. So I know that I taught you guys geometry, and I know that we didn't we do symmetry, or what is it called? Not symmetry, it's called proportions, proportional? Yeah, proportional triangles. Do you guys see proportional triangle there in blue, and then this one in green? Look at this one in green. Yeah. So look, I'm going to write R over H is to 5 over 10. But I know what H is. What's the height of the water? I thought it was 6. Yeah. So the height of the water is 6. So then to find R is just going to be, let's see, 6 times 5 is 30 divided by 10. So R is just 3. Do you see how we got it, guys? Okay. Now, real quick, I'm going to come back, and I'm going to also do this. R is also equal to, this was an H. And I'll put the 6 there.
But why are we finding the radius when the water's at 6 feet? We're not even using dHdt.
But I need the radius because, look, I need the radius and I need drdt. I cannot solve for dHdt. This is all I have. Everything in green is that I have. I have the dVdt. I don't have the radius directly. I'm looking for dHdt. I have the height.
So I'm saying, like, if we're using the radius at 6 feet.
When h is 6 feet.
Yes, when h is 6 feet. Then are we just solving for dHdt?
Yeah, we're solving for DHDT when the height is 6 feet.
DHDT 6?
No,
No, we're supposed to be finding like.
DHDT is how fast it's moving.
Yeah. But
H is 6.
because H is in position.
Yeah.
and DHDT is the velocity.
DHDT is velocity, how fast it's moving. How fast it's climbing up. Does that make sense? Okay. All right, guys, real quick. 10R is equal to 5H. So that means R is equal to H over 2 or 1/2 H. Does that make sense to you guys? Okay. So I can write this. I'm going to take a derivative here. dr dt is equal to 1/2 dH dt. Does that make sense to you guys? All right. So here's what I'm going to do. You see this dr dt in red? What do you think I'm going to do to that? I'm going to what? Starts with the letter S. Substitute. I'm going to substitute my 1/2 dH dt. Cool or not cool? All right, so here we go. Finally, here's how our new model looks now. dV dt is equal to pi over 3 bracket r squared dH dt, which is what I'm looking for, plus 2 times h times r times 1/2 dH dt. So now the half and the 2 go away, and I have pi over 3 r squared dH dt plus hr dH dt. Now I can plug in everything. That's dV dt. Let's plug in everything, guys. What was my dV dt? Was it 9? Yeah, it was 9. Not everyone at the same time. Okay. Catch up and then we'll start. What was the radius of the water? 3. So 3 squared is 9 dH dt plus the height of the water was 6. The radius was 3 dH dt. And you're done with calculus. Now it just turns to, yeah. So let's see if I can do this really quick. I'm going to write 9 equals pi over 3 bracket 6 times 3, 6, 12, 18. 18 plus 9 is 27. So I'm going to write as 27 dH dt. And then 3 goes into 27 9 times. So can I say 9 pi? 9 pi dH dt. And then finally, 9 equals 9 pi dH dt. To get the dH dt by itself, we got to divide by 9 pi. 9 pi. 9's cancel out. The dH dt, 1 over pi. And let's put units on this. What is this? Feet per minute. No, just feet per minute. Yeah, it's DHET, how fast it's rising, how fast it's going up. Feet per minute. Volume is cubic feet per minute. You know what I mean? If you were to put all the units in here, it would work out. As long as our units are consistent, and they are. How do we feel? How do we feel? Do we feel okay? All right. Don't worry, we're almost done. This one, you're probably going to hate me. I don't know. Is there another way to do example 5? So look how much of it took the whole page to do example 5. Is there another way to do it? Yeah. Another way to have done it, guys, is this. You see this in green, I guess in black now. That's really the key. So watch. I could have said volume equals pi over 3 r squared h. I'm not taking the derivative yet. Yeah. I'm not taking the derivative yet. And they want dH dt, so that means I'm going to get my volume equation only in terms of h. So I don't even do anything yet. So didn't we tell you that r over h equals 5 over 10? So look, right here, I could have just done this. I could have said cross multiply 10, r equals 5h, and then divide by 10, divide by 10. R equals H over 2. And I could do direct substitution right there. We better get the same answer. It would suck if we don't get the same answer. So look, here we go. I'm not taking the derivative yet. I'm going to write H over 2, close it, squared, because that's what R is, times H. So pi over 3. H times H is H squared. 2 times 2 is 4. H squared over 4 times H. And look, I haven't taken any derivatives yet. And H cubed over 4. Finally, let's just simplify this. Pi over 12 H cubed. Chavez, I don't understand what you're doing. I have no idea. I'm just writing everything down because you're going way too fast. Okay, I'm going to slow down. The whole point, okay, you guys are almost done. Fast forward this twice the speed really quick, YouTube fans. Okay, now slow down. All right, stop. All right, the whole point of all this, I just want to know how fast this is moving, the water, right? So isn't that just dHdt? Look, I already got my volume in terms of height. All I got to do is take a derivative right off the bat. dV dt is equal to my derivative, the pi over 12 is a constant, 3 pi over 12 h squared times the derivative of h, which is dH dt. OMG, I already have h, I already have dV dt. This guy reduces, 3 goes into 12 4 times. So now, here it is, dV dt, let me rewrite it one more time real quick. Pi over 4, oh wait, yeah, h squared dH dt. I'm going to plug in what I know. dV dt was 9. H was 6. And I want to get dH dt. 9 equals 6 squared is 36. So 36 pi over 4 dH dt. Yep, that does reduce. So I have 9 equals 9 pi dH dt. OMG, look at that. Divide by 9 pi, divide by 9 pi. dH dt equals 1 over pi. Feet per minute. Was that easier? I thought it was. So what's the whole point of all this, guys? There's many ways to get an answer. You're the engineer. You're the future. You're the future scientist. You're the future doctor. You're the future. There's always another way. So when you become that medical doctor and someone tells you, oh, it's not possible, then you, being the medical doctor, figure out another way to help that patient. You, being the engineer, figure out another way, an easier way to figure these things out. Cool or not cool? Cool. All right, that concludes this session, guys. Let me give you your activity, and that's it. Stop recording.